Hello and welcome to today's lesson where we're going to take an introductory look to some of the concepts that you'll cover in particle physics during AQA A-Level Physics. So in this particular lesson we're going to try and understand the basics of particle physics. So the first thing to consider when looking at particles is how can you distinguish between different properties of particles. So how is a proton different to a neutron and how is it different to an electron? Now here are the following ways any particle in the universe can be described: by its energy or mass, its charge, its spin, its strangeness, its lepton number or its baryon number. Now there's only two properties that you've come across at GCSE: energy or mass and charge. The other ones, lepton number, baryon number, strangeness and spin, are all new concepts for A-level. Now, actually spin technically is a concept we cover actually degree level, but the other ones you'll come across later in the course is ways to describe different particles. So the ways you can describe a particle are energy or mass, charge, baryon number, lepton number, spin and strangeness. Now in this lesson we're going to investigate mass and specific charge in particular. So for example, if you wanted to describe a proton, you could describe it by the following different properties. Now the first thing you'll notice is that mass and charge no longer come in simplified units of saying a proton has a charge of 1 and a mass of 1. Now we've got to go with base properties and base units, so we consider things like coulombs and kilograms. So we're going to investigate how those work. Now one method of differentiating between particles is by measuring the mass. Now we find that the SI unit of mass, the kilogram, can be difficult to work in because the mass in kilograms of any one particle is going to be very small. So we do use some other units when we cover mass of particles. Now one of the most commonly used units is MeV over c squared, or mega electron volts over c squared. Now again, that's not an SI unit, but sometimes we use it in particle physics because it gives us a nice round whole number or large number to actually work with. So not working in times 10 to the minus 27s, we're actually working in 10s and 20s and 40s and 50s. Okay, now the other way you can measure it is in something called U's. Now you've come across U's before in chemistry because we define a U as 1/12 of the mass of an unbound neutral atom of carbon 12. So in theory, carbon 12 will have a mass of 12U. Now you'll see here the conversion factor between the U and the kilogram. Now that's very important because you've got to be able to convert in between the conversion factors in A-level physics. Now you'll be pleased to know that you won't have to memorize these conversion factors. They are given to you in your examination, in your equation book. You've just got to be able to use them and convert them. So a question might say, what's 17 MeV over c squared in kilograms, or what's 4U in kilograms? Now to go from a non-SI or standard unit to an SI or standard unit, you multiply by the conversion factor. So you'll see in both examples we multiplied by the conversion factor to convert our value into kilograms. Now the MeV over c squared units are a unit of mass because they come from the E equals mc squared formula. So m is equal to E over c squared, and the energy in this example is measured in mega electron volts, which is where it's derived from. Whilst these units are simplification units, so for example in year 10 and year 11 you said that the proton had a mass of 1, it was actually 1U. So that's where those come from. Now, if you wanted to go out of a standard unit, out of SI, and into a non-SI unit, such as MeV over c squared or U, you no longer multiply by the conversion factor, you times by the conversion factor. Now, you'll notice straight away, if you look through these values, you'll notice that the reason why we select MEV over c squared and the reason why we select U is because it gives nice easy numbers to work with. So for example, 2 times 10 to the minus 29 kilograms becomes 11.2 MEV over c squared, and 4 times 10 to the minus 26 kilograms becomes 24.1 U. Nice easy numbers to work in. Now, that unfortunately though isn't really absolute in physics, because really when we're looking at things like charge, for example, we can't really place them in relative charge anymore, such as +1, -1 or 0. We've got to express charge in terms of coulombs, the SI derived unit for charge, the standard unit of charge. So whilst the proton at GCSE you said was +1, okay, and the electron was -1 and the neutron was 0, we now actually say that the charge of a proton is 1.6 times 10 to the minus 19 coulombs, because 1 unit of relative charge at GCSE is actually 1.6 times 10 to the minus 19 coulombs. So a proton has a charge of plus 1.6 times 10 to the minus 19 coulombs, an electron has minus 1.6 times 10 to the minus 19 coulombs, and obviously your neutron still has 0 coulombs of charge. Now you should memorize this particular conversion factor moving forward, because it'll be really helpful when you answer questions. Now, whilst charge is a really useful quantity, there's an even more useful quantity, and that's something called the charge to mass ratio of a particle. Now, like at GCSE, when we said we had specific latent heat or specific heat capacity, the specific meant per kilogram. So now we call the charge to mass, the charge per kilogram, the specific charge of a particle. Now, this property influences a particle's behavior. It tells you how much a particle will be deflected by in an electrical field. The larger the specific charge, the greater the deflection in the electrical field. The smaller the specific charge, the lower the deflection in the electrical field. Now, if there's no specific charge, it won't deflect at all. Now, like we mentioned before, this will allow you to also work out a magnetic field, because a magnetic field and an electrical field work by the same rationale. Now, to work out the specific charge of a particle, its specific charge equals charge divided by mass, because specific means per kilogram or per unit mass. So whilst our unit of charge is in coulombs and our unit of mass is in kilograms, the unit of specific charge is coulombs per kilogram. Now, this indicates how much the particle will deflect in an electrical or magnetic field. So like we said before, the larger the specific charge, the greater the deflection. But this is not given to you. You've got to memorize this particular equation. So you've got to just learn this off by heart. So there is an example of carrying this out. Now you will notice that you need to place your charge in coulombs and your mass in kilograms and work it through like that. So our charge has been placed in coulombs, our mass has been placed in kilograms, so you can work it through like so. So just always remember to have your charge in coulombs and your mass in kilograms. Now, because specific charge is a scalar quantity, you don't actually need to include minus signs in answers, because you don't have to give the direction. Now again, just remember, if it's got an ion of +2, you've just got to make sure you convert that unit of relative charge to your value in coulombs. So now, the next concept we're going to cover in particle physics is what we call the fundamental interactions. So there are actually 4 fundamental interactions in nature. There's gravity, the weakest interaction in the universe, which has an infinite range. It's the interaction that causes planets to rotate and you to be attracted to the surface of the Earth. We've got the weak nuclear interaction, which causes radiation in atoms. We've got the electromagnetic interaction, which has an infinite range but only works on charged particles, and it causes electricity, it causes magnetism, it causes attraction and repulsion. And finally, you've got the strong nuclear interaction, the strongest interaction in the universe, okay, which is the interaction that holds nucleons together, and it only works on hadrons. Now, hadrons are particles which are made out of quarks. Now, for example, the proton is made out of 3 quarks, so it's a hadron. The neutron is made out of 3 quarks, so it's a hadron. So anything which is made out of quarks, which is a smaller particle than what you covered at GCSE, is affected by this strong nuclear interaction. Now, we can sum up their properties with the following information. So the maximum range of the strong nuclear interaction is about 10 to the minus 15 meters, but it's extremely strong. The electromagnetic interaction has a range of infinity, but is about 100 times weaker than the strong nuclear interaction. The weak nuclear interaction only works of a range of about 10 to the minus 18 meters, but we're looking at 10 million times smaller than the strong nuclear interaction. And then finally, you've got the gravitational interaction, which has an infinite range, but is an extremely weak interaction. Now, you've got to remember these different properties of interactions for your examination. But why do we have different interactions causing different properties? Why have 4 interactions? Why do they have different properties? What's actually going on? Well, we actually think a force is produced by an exchange of a particle, which we call a boson, between objects in the universe. So this is what's happening on the microscopic scale, which produces the macroscopic or real world force. So what is happening is these bosons are being exchanged between objects, so we call them exchange particles. So in this example, between 2 magnets, exchange particles being exchanged between the 2 magnets, so that produces the force of electromagnetism between them. So you've got your exchange particles. Now, basically, another name for an exchange particle we call in physics a virtual particle. We call them virtual particles because these exchange particles can only exist for a short amount of time, because the energy needed to make them, to create them, is borrowed from the universe. Now, you might think, can you create energy? Well, no, you can't, but the technical rule is that energy must be conserved over an average value of time. So if we create these exchange particles, they have to only exist for a short amount of time before we've got to repay the universe, and we've got to put the energy back into the universe so energy is conserved. So basically, they can be created out of the universe, but they can only exist for a short amount of time. Now, this is an extremely important idea, because the larger the exchange particle, the more energy needed to be borrowed from the universe to produce it, so the shorter the time it can exist before the energy needs to be paid back. So the range of that exchange particle is shorter, so the range of the force it produces is a lot smaller. Now, if an exchange particle has no mass, no energy needs to be borrowed from the universe, so therefore that exchange particle can exist forever, so the range of the force it produces is infinite. So why is the electromagnetic force and the gravitational force infinite in range? It's because the exchange particles that produce the interaction are in fact massless. Now, another reason why we call these particles virtual particles is because we can't ever observe them directly, because they are producing a force by being exchanged between 2 objects. So if you pluck this particular virtual particle out of the universe before it reaches the object it's intended to, it would no longer produce a force and therefore would cease to exist. So the act of trying to observe it would cease it from existing. The energy would just go straight into the universe. So we can never observe exchange particles directly. We can only observe the effect of an exchange particle. So basically, in 1935, we made the discovery that forces occur in the universe due to the exchange of particles called bosons or virtual particles. Now, these particles are virtual because we can't directly detect them, and if they were intercepted, they would stop the force from acting. Now, basically, what we realized is forces occur because these exchange particles are being exchanged between 2 objects, causing a force to be produced on the macroscopic level. So the properties of an exchange particle lead to the properties of the force, but exchange particles cannot be observed directly. Now, you can have an exchange particle causing repulsive force because you can think of it a bit like 2 people on roller skates or skateboard or ice skates, okay, that throw a ball to each other. So if person A throws a ball to person B, person A slides back when they release it, and person B moves back when they catch it to conserve momentum, and it's the same process that means that 2 objects can have a repulsive force between them when they exchange an exchange particle. So there's got our repulsive force being caused by the exchange of an exchange particle. Now, to have an attractive force, you've got to imagine now that these 2 people on skateboards or roller skates or ice skates have now got the backs to each other, and they throw a boomerang between each other. Now, in this example, A is going to move towards B when they throw the boomerang. B is going to move towards A when they catch the boomerang. So to conserve momentum, they move towards each other, and that causes an attractive force. So what do we know? Basically, bosons are virtual particles which exist for a finite amount of time and space, and they can't be directly detected, otherwise the particles would disappear back into the universe. So, as a result, in the standard model, we know about three varieties of bosons. The photon, that's the exchange particle that produces the electromagnetic interaction. W and Z bosons, which can cause the weak nuclear interaction, and gluons and pions that can cause the strong nuclear interaction. So these exchange particles can cause the force on a macroscopic scale. Now, we have never actually discovered the graviton, which is the exchange particle for the gravitational interaction. Now, we think that could be because it hasn't been discovered yet due to the weak nature of gravitational interaction, so it's very difficult to indirectly detect a graviton. However, some physicists believe that this is because the gravitons don't actually exist because gravity doesn't work via a particle exchange interaction. It might work by something else. Now, technically, another name for a gluon is a pion, because we say that the gluon mediates the strong interaction between the particles, so protons and neutrons, but we say a pion mediates the strong force between the quarks that make up a particle. So it's just a different name for the same exchange particle. Now, let's just recap our properties. The graviton, the exchange particle for gravitation, it's never been directly observed. The photon, the exchange particle for electromagnetism, it's got no mass, so an infinite range. So the electromagnetic force has an infinite range. The gluon, which is the exchange particle for the strong interaction. So it's a massive particle, so it can only exist for a short period of time. So it's only got a short range of interaction. So that means that the strong interaction has a very short range. And here you've got your W and Z boson, which is the exchange particle for the weak interaction. Now there are three bosons because it's for a really complicated reason. It's to allow something which is called quantum isospin and hypercharge to be conserved, but we'll not concern ourselves like that's degree level physics. And then the W boson is the largest exchange particle, so has the shortest range because it exists for the shortest amount of time. So the weak force has a very, very, very short range. Now, in the 1960s and 1970s, when physicists were trying to explain their work on exchange particles to the general public, they realized to their great dismay that the general public didn't understand this concept of exchange particles. So enter Richard Feynman, who tried to make physics understandable to all. So to make physics more understandable to all, he came up with one of his greatest inventions, the Feynman diagram. Now, these are diagrams used to describe and show particle interactions and decays produced by exchange particles. Now, what you've got on your y-axis is time, and on your x-axis is distance. Now, basically, it shows how two particles can interact and change over time in the universe. It's not a graph, rather it's a diagram to help people understand what's going on. Now, if we see an arrow going backwards in time, that doesn't mean time's going the other direction. It just means we've got something called an antiparticle, which is a particle with the same mass as a particle, but opposite other properties. So, for example, an anti-electron will have a positive charge. So you can see it through like that. So in our Feynman diagram, we've got the past, which occurs at the bottom, the present, which is when the exchange particle is exchanged to cause the force, and then you've got the future, what happens due to this force occurring. So let's work this through. So what are the rules of the Feynman diagram? Time goes up vertically, space goes along horizontally, particles are shown by arrows. If the particles are stationary, you draw a vertical arrow. If the particles are moving, you draw a slanted arrow. To show an interaction, a force, you draw a wavy line to indicate an exchange particle, and then you draw the particles after that. So you can work out each one. Now, if an interaction is caused by attraction or repulsion, the force is electromagnetism, so the exchange particle must be the photon. If the interaction is between hadrons, things made from quarks, and there's no leptons, things not made from quarks, the force must be the strong nuclear interaction, so the exchange particle is the gluon, or the pion. And if the the interaction includes leptons and the particles change type, then the force must be the weak nuclear interaction, so the exchange particle is a W with a Z. Now, a lepton is a particle that's fundamental, it's not made from quarks. An example of this is the electron. Now, the stronger the force, the faster the interaction. So if your interaction occurs by the strong interaction, it occurs a lot faster. If it occurs by the weak interaction, it occurs a lot slower. Alpha decay occurs by the strong interaction, so it's very fast. Beta decay occurs by the weak interaction, it can be quite slow. So, now finally, to work out which one of the W bosons you would have in the weak interaction, if you look at your starting particle, and if it's positive and it's become neutral, it's thrown away its positive charge, so we say it's the W positive boson. If it's negative and become neutral, it's thrown away its negative charge, so the W negative boson has been used. If it's neutral and become positive, it's lost its negative, so it's the W negative boson. And if it's neutral and becomes negative, it's lost its positive, so it's the W plus boson. So here's an example of the Feynman diagram. So what we've got a proton and a neutron attracted to each other by the exchange of a pion, and therefore it's then producing two baryons. So it must be by the strong interaction, because there's no leptons, all the things are made from quarks, there's no leptons present, no particles change type, so it's by the strong interaction and it's a fast process. Here, what's happening? Two electrons are repelled from each other. Now, what exchange particle are they exchanging? Well, they're exchanging the photon, so they're interacting via the electromagnetic repulsion. Here, what's happening? A neutron is turned into a proton, and it's producing an electron and another particle, which we'll get onto in a bit. And therefore, we've got something changing type. We've got particles there which are not made from quarks, the electron, so therefore it must be by the weak, and because it's a neutral going positive, it's thrown away its negativity, so it's the W minus boson. It's a slow process. Here, the protons turn into the neutron and produce a positive electron or a positron and another particle. So what's happening here? Well, we've got particles that are not made from quarks here, and we've also got a particle change in type, so it must be the weak interaction. The proton is going to a neutral neutron, so it must be a W positive boson. But because it's by the weak interaction, it's a slow process. Now, the next thing we want to look at is the idea of the atom. Now, the atom, as you'll know from GCSE, is predominantly empty space. Now, the radius of an atom is about 10 to the minus 12 meters, and the radius of the nucleus is 10 to the minus 15 meters. So the radius of the atom is about 10,000 times bigger than the radius of the nucleus. But why is that? Now, basically, if you consider the forces we've just looked at, if there was only the gravitational force and the electrical forces, well, what would happen is the electromagnetic force is very large, which is causing repulsion. The gravity is quite weak in comparison, so therefore the nucleus should absolutely obliterate itself and should never be there. Okay, now we've got to look at the following though, because there's also in fact a force called the strong nuclear force, which is holding all the nucleons in the nucleus together. Now, the strong force keeps the nucleus together. Now, the nucleus can only be of similar size as the range of the strong force. Now, the strong force, as the name suggests, is much more dominant than the electromagnetic force found in the nucleus. So there's a very dominant force keeping the nucleus together. There's a small force trying to repel it out in comparison, so a nucleus will form in the atom. Now, if the attractive strong force overcomes the repulsion of the protons, okay, that will hold it together, because without the strong force, the nucleus cannot be held together. Now, the strong force can only act between quarks. So particles called hadrons, which simplify into baryons, 3 quarks, or mesons, 1 quark, 1 antiquark, are affected by the strong force. Leptons, like electrons, are not made from quarks, so are not affected by the strong force. Now, the strong force occurs with the exchange of gluons between the particles But like we know before, because the gluon has a mass, it can only exist for a short amount of time, so it can only cover 10 to the minus 15 meters. So it can't actually travel that far. Now, it works in between quarks in a particle as well as in between particles because they are smaller than 10 to the minus 15 meters away from each other. So as a result, it can still work on the quark scale as well. Now, the strong force has the following properties. It's got a range of about 3 to 4 times 10 to the minus 15 meters. Now, the prefix of 10 to the minus 15 is femto. So 10 to the minus 15 can also be written as femto. Now, that's about the range of the diameter of a small nucleus, which is not a coincidence. Now, the strong force is attractive from about 4 femtometers to about 0.5 femtometers, but less than 0.5 femtometers, it's repulsive to prevent nucleons such as neutrons and protons pushing into each other. Now, the strong force has these properties because of the exchange particle that produces it, the gluon or the pion. So, what would make a nucleus stable or unstable? Well, basically, if we know that the strong force is approximately the same strength as the electromagnetic force, well, the two forces are closely balanced like a seesaw. It's tipping one way and then the other. So therefore, the nucleus is unstable. The nucleus is susceptible to a radioactive decay, alpha, beta, or gamma. But if the strong force is much larger than electromagnetism, it will therefore be a stable nucleus. The nucleus will not decay. The nucleus will not undergo alpha, beta, or gamma decay. Now, if the electromagnetic force was a lot larger than the strong force, then the nucleus would never form because the repulsive force will be larger than the attractive strong force. So, let's consider this idea. Now, how can we make the strong force much larger than electromagnetism? Well, for small nuclei, you just have the number of protons equal the number of neutrons. Well, why is that? Well, number one, only protons experience electromagnetism because it's got a charge. Neutrons don't, so they would have no electromagnetic force. Secondly, neutrons will have the strong force and protons will have the strong force because they're both made from quarks, so you've got double the number of particles that can experience the strong force compared to the electromagnetic force, so you've got a much larger strong force. And then in addition to that, the strong force is stronger anyway, so it makes it even more stronger as a force. Now, for large nuclei, though, we've got an issue because if your number of neutrons equals the number of protons, it's actually about equal in size. So you've actually got an unstable nucleus. Well, why is that? Well, it's because the strong force has a range, 10 to the minus 15 meters. And in a large nucleus, the nucleons on either side of the nucleus are more than 10 to the minus 15 meters away from each other, so they can't attract each other by the strong force, but they'll still repel each other by the electromagnetic force because that has an infinite range. So the electromagnetic force is the same size, but the strong force will decrease until they're about the same size. So for large nuclei, if you want a stable nucleus, you need lots and lots of neutrons in there. A lot more neutrons than protons. Because if you pack all these neutrons into the nucleus, they're all going to be within 10 to the minus 15 meters of each other. So they'll all still attract each other by the strong interaction, and then that will cancel out or will be greater than the repulsive force of the electromagnetic force. So the strong force is much larger than the electromagnetic force. You've got a stable nucleus. Okay, and that allows us to have our large nuclei. Okay, so that's very important. But that's also why the size of the nucleus can only be approximately the size of the strong force range, because this pile of the neutrons in there is only a short-term fix. It can only do for so more before the electromagnetic force is more repulsive again, so it only can be for a limited size, which is why the nucleus is so small in the atom. So to summarize this information, if the strong force is a lot greater than electromagnetism, nucleus stable. If the strong force is about the same as electromagnetism, nucleus unstable. If the electromagnetism is greater than the strong force, nucleus never forms. But what happens if the nucleus is unstable? Well, let's just consider what's going on first with the strong force. So the strong force can change its properties. So just remember, okay, at distances greater than 4 femtometers, 4 times 10 to the minus 15 meters, the electrostatic repulsion is dominant, the nucleus can't form. Now, at distances less than 0.5 femtometers, the strong force is repulsive, so the nucleon stays separate. Okay, and so far we've got the following here. So at distances larger than 4 times 10 to the minus 15 meters, the strong force doesn't exist, which is why nuclei can't be much larger than 5 times 10 to the minus 15 meters, because the strong force can't overcome that electromagnetic force. Between 1 and 4 femtometers, 10 to the minus 15 meters, the strong force is strongly attractive. That makes the nucleons stick together and a stable nuclei form. And smaller than 0.5 times 10 to the minus 15 meters, the strong force becomes repulsive. It ensures the nucleons don't get crushed and exist as neutrons and protons. But like we said before, what happens when a nucleus becomes unstable? Well, there are 3 different processes an unstable nucleus can undergo. Alpha emission, which on an alpha particle, a helium nucleus, is ejected from the parent nucleus. So you lose 2 protons, 2 neutrons. Now we form a new element because there's a new number of protons in the nucleus. Now, whilst this is the same as a helium nucleus, the term alpha particle is used if the particle has originated from the nucleus. Now again, this is an example of transmutation because we've got a new number of protons in the nucleus, a new element is formed, 2 places lower on the periodic table than the starting element. Now each alpha particle is released with the same kinetic energy as there's no other products produced in the decay. There's only the alpha particle being emitted. So here's our demonstration of alpha particle emission going on. Now, in beta decay, now that it's actually the one in GC we covered is actually called beta minus decay. Well, what happens is a neutron changes into a proton, okay, via an exchange particle and produces an electron. Now the proton stays in the nucleus. The electron leaves the atom as a high energy beta particle. Now this has got to be the weak interaction because it involves leptons, things not made from quarks, and it involves something changing type. So what's actually going on? Well, it means that the atomic mass number stays the same because you've still got the same number of protons and neutrons, but the atomic number has gone up by 1 because you've increased your numbers of protons by 1 because a neutron has turned into a proton. So in beta minus emission, a neutron is transformed into a proton and an electron is emitted. Now beta minus emitters are found naturally in the universe, but you can also make them by bombarding stable isotopes with neutrons. Now it's a new element because we've got a different number of neutrons. Now whilst it's the same as an electron, beta is used if it's originated from the nucleus, and again it's an example of transmutation. It's formed an element 1 place higher on the periodic table compared to the parent nucleus. Now, we've already just mentioned that, so here's an example of what's going on. Your neutron turns into a proton and it makes an electron. Now, beta plus emission is the opposite way around. A proton is transformed into a neutron. Okay, so it's the opposite one that takes place. So here, a new element must be formed as we've got a different number of protons. Now, again, we're using beta as our term because the electron has come from the nucleus, and again, it's an example of transmutation. It forms an element 1 place lower on the periodic table. Okay, so we don't tend to find these naturally in the universe. You've got to artificially make them. And the last type of decay you can have is gamma decay. That's where there's no change in the makeup of the particles of the nucleus. It just loses energy in the form of an energy particle that we call the photon. So basically, gamma emission is often an event that happens after alpha emission. So after alpha emission has happened, the daughter nuclei are left with an excess amount of energy, which we call an excited state, which will then lose at some point. So will go from excited state to ground state, its small state in equilibrium, and as it does this, it releases energy, which we call a gamma photon. And because there's no nuclear structure change, there's no change in the number of protons, there's no change in the number of protons or electrons, it's just a change of energy. So it's not an example of transmutation as no new element is formed. Now a nucleus which has an excess energy before gamma decay, so after alpha emission and you're awaiting gamma emission, we call that a metastable state. So this is a demonstration of a gamma ray emission. And with that, okay, it obviously will occur after alpha emission. And with that, we've covered all of the particular parts of the introductory section on particle physics for A-level. Now, obviously, this is not the entire course for particle physics in A-level. It's just a taster to see what it's like. If you want to read up on things further, you can read up on what a lepton is, what a baryon is, what a meson is in a bit more detail, and also you can read up on quark theory as well, because they're all very interesting parts which leads to a fundamental principle which we call the particle zoo of physics, which is something you may wish to read up on. So thank you very, very much for listening to today's lesson, okay, and have a lovely day.